Let's have a look now to see how light behaves when it hits a curved surface. I've got two curved surfaces here, two concave mirrors. So I'll position this one here. And what you can see is that the rays of light which come parallel here strike the surface and are directed towards a single point. Now that point is called the focal point. So what I'm going to do is just trace around this mirror, first of all. A bit tricky to keep it in the one spot. So there's the surface, and I'll put dots here to mark the position of the ray. So that's ray 1 and its reflection. Ray 1. Over here, ray 2. I think I've moved that slightly. So that's the second ray, and its reflection is right back, so that's 2. And the third ray is this one here, so 1, 2, 3, 4 dots there, and its reflection is there. This is ray 3. What I'm going to do now is remove this and then redraw or draw in the actual rays. So those rays those rays have been drawn in now, and my next task is to measure the focal length. So I'll put the ruler in place and measure that focal length there at what looks like 2.3. The next task then is to have a look at the focal length of another mirror, and this time the mirror has a slightly different shape. It's more spherical. So I'll position that there, and again, as I did before, one of the things that I'll do is to trace around or trace the mirror. So, holding this as firmly as I can. Putting in some dots now to mark where the rays are. So that's ray 1, and that's where reflected ray 1 is. Ray 2, now ray 2 is directed right back, so that's 2. Ray 3 is here. And it's reflected here. So that's 3 there. I'll now redraw or reposition the lines, the rays. So I've done that, and I probably should put some arrows here to show the direction of the rays. And what I want to do now is to have a look at this focal length here. So again, positioning or getting the ruler and putting that in place. And what do I find? I find that length there is very close to 1.9 centimeters. When we have a look at this question here, explain how the shape of the concave mirror changes with the focal length of the mirror. Well, if we have a look at this one here is the focal length is shorter compared with the focal length of this one here. Now, what we've got here, this mirror here is what we'd call a parabolic mirror. This one here is spherical. But in general, what we can have a look at when we have a look at these is a radius. A radius is more accurately appropriated to this spherical mirror. But the focal point here is what's called half the radius. The distance of the focal point is half the radius of curvature. So if I've got a radius here, so the focal length is generally half the radius of curvature. And here again, the radius of curvature would be about twice that. So what we've got here is a smaller radius of curvature, and that gives us a shorter focal length. Let's have a look now at the convex mirror. We're ready now to have a look at what happens when parallel rays hit a convex mirror. And what I'll do is hold this in place as best I can and draw the rays of light, and first of all, of course, draw the mirror, and then put these dots here to mark the position of the rays. So having traced in those rays, the next bit of instruction here is to label the focal point on your diagram. Well, in order to try to find the focal point, what we've got to do is trace these rays back. That's where we'll find the focal point. So if I go like this, just using a dotted line, and here ray 2, it seems to have come from here. So that's tracing this one, and then this one here. Now you can see I haven't quite got that coming from a precise point, largely because it's fairly easy to move that mirror and change the angles quite slightly. But we can have a look and gauge the focal length. So moving my ruler into place here, that looks to be around about 2.4. So 2.4 there. Maybe a slight error, parallax error there, because I'm looking at this at an angle. And our next one is to have a look at the one with the smaller focal length, or the smaller radius of curvature. So again, I'll go through the same process. What I'll do is position this so that the second ray, the middle ray, is reflecting right back along the axis. So again, I've drawn in these rays, and I should put little arrows in here to show the direction of those rays. And what I'm asked for here is the focal length. So what I've got to do is see where those rays seem to be coming from. So again, I'll draw a dotted line going back there, here a dotted line going back here, and from here dotted line there. So again, what I can do is measure that focal length. So positioning that, again looking at this from an angle, that looks to me to be somewhere around 2 or 1.9. Again, I've got a bit of parallax error here. .9 I think might be the most accurate, so I'll write that in. Having a look now then at this question, explain how the shape of the convex mirror changes the focal length of the mirror. Well, as you can see, this one, which is got a smaller radius of curvature, produces a focal length that is shorter than this one here, which has a larger radius of curvature. Again, looking at this second question, compare the location of the focal point for the concave convex mirror. Well, you can see here that the focal point is actually behind the mirror, whereas in the case of the concave lens, the focal length was in front of the mirror. Now, one of the things that we can, one of the points that we can make from this is that this focal point here, which is behind, in which we had to trace these rays back, this is called a virtual focus. This is a virtual focus. Now, the other one that we had was a real focus. And what that means in practice is that if we were trying to project the image that we can see as we look at a mirror like this, the image that we would see could not be projected onto a screen. And this is what we're talking about when we're talking about real images. Real images are ones which can be reflected onto a screen. So if I took this, for example, going back to the concave mirror, I could put some sort of screen here and have the rays of light actually hitting that screen. But in the case of a convex mirror, those rays of light will never be able to be projected onto a screen. So, if that is the case, it is a virtual image. If it can be projected onto a screen, it is called a real image. So this is the point of what we're looking at here. This next part, what is this experiment about? Well, hopefully you can put that into your own words and write a summary there. Again, for the conclusion, write a conclusion for this experiment summarising what you did. So do that very, very briefly, and the results that you got. So you should be able to say something here about a virtual image and the focal length and the shape of these lenses and the shape of these mirrors, how they affect the focal length. So just to go back over what we've been looking at, you can see here the rays of light as they hit the concave mirror come to a point. Now, the focus. This is what we call creating a real image. A real image like this can be projected onto a screen. In contrast to this, the image that this one here, our concave mirror generates, we find the focal point comes or is located behind the mirror. Now that indicates that this image would not be able to be projected onto a screen, and this we call a virtual image. So it seems to be coming from behind here, which of course it isn't. That makes it a virtual image. Now we see a similar kind of thing illustrated when we have parallel rays of light coming through. This is a convex lens here, and you can see that we've got a focal point there. So if they're meeting there, that would create a real image. Again, with another lens like this, we've got a real image. That real image would be projectable onto a screen. In contrast, a concave lens would in fact create rays of light which seem to come from back here, a focal point back. In other words, what we're creating there is a virtual image again. So to summarise, what we've seen in this experiment is, first of all, the notion of a focal point, a radius of curvature, and virtual images and real images. I hope you found it worthwhile.